Okay. I want to say something about the method of characteristics. So consider a general second-order semi-linear PDE. It's second order because it involves second partial derivatives. Okay, and for the highest order, second orders, we have coefficients on A, B, C. But for lower order partial derivatives like UT and UX, it is possible that you have a nonlinearity. Okay, so F can be a highly nonlinear function involving x coordinate, t coordinate, and the unknown function u, as well as the first partial derivatives of u with respect to t and x itself. So it is called the semi-linear. Okay, in the textbook, the author call such PD as quasi-linear. Actually, it's in mathematics. Actually, people usually use semi-linear linearity to describe such kind of PDE. Okay, because for quasi-linear PDE, the coefficient may depend on u and ut and u sub x. So it's more general. All right. So I prefer to coherent with to be coherent with the majority in the mathematics. Okay. So we consider such a linear, semi-linear PDE. Okay. All right. Now. The semi-linear PDE, so it's called 12.4. I forgot how many equations we have already up to now. How many? 5. So this could be 6, right? If I'm wrong, yeah, thank you. Okay, so this is the 6th one. Now, so the semi-linear PDE in 12.4.6, okay, is said to be hyperbolic or parabolic or elliptic. Okay, at the point x0, t0. Okay, according as the v square, the v, okay, it's x0, t0 minus 4 times a, x0, t0, and c, x0, t0. Right? So it's positive 0 or negative. Okay, respectively. This terminology is from an analogy to the conic sections. You know the conic sections, we consider hyperbola, parabola, and elliptic curves, right? In high school. Okay. So, remark. A conic section can be described Okay. Can be described by the quadratic equations in xy. Right? So we have a x squared bxy cy squared bx dy. Okay? So in general, a conic section can be described by quadratic equations. Okay? And so we know by coordinate transform, we can reduce such a quadratic equation, all right, to standard form. Okay, so first, if b squared minus 4ac is greater than 0, then this comes to like a cubed x squared minus, so this comes to hyperbola. Okay. The second one is if b squared minus 4ac equals 0, then this comes to parabola. Okay. And if b squared minus 4ac is less than 0, then we have this. Okay. So actually the coordinate transform is a linear transformation. Okay, it's a linear transformation, and so and it depends on the b squared minus 4ac, the discriminant of the quadratic equation. So compare with that. This is the reason why we call such a PDE to be parabolic, or elliptic at a point, according to the value of this formula. Okay. Now, if the semi linear PDE is hyperbolic or parabolic or elliptic. At every point in a region of the XT plane, it is said to be hyperbolic, parabolic, or elliptic in that region. Okay, so a semi-linear PDE sometimes is hyperbolic, okay, in some region. Sometimes it is parabolic in another region, and it is elliptic to another region, right? So other regions. Okay, and this is because that b square minus 4ac is a function of s and t. Okay, so the value has to change. Okay. Okay. All right. So okay. So just like in the study of conic sections. We transform a quadratic equation into standard forms, all right, by using coordinate transformation. So actually, we use coordinate transformation, right? So, similarly, we can transform the xt coordinates into other coordinate system, so that we can simplify this PDE. For example, we learn from Lambert's solution for the wave equation. We actually transform the x and t to v and w, right, by a linear transformation. Okay, and with such spatial linear transformations, we find that we can transform the wave equation into an equation involve only the mixed partial, second order partial derivatives. Okay, and we are able to solve this spatial partial differential equation easily, right? So, so our purpose is that can we find the coordinate transformation such that the coefficients of this term and coefficient of this term become zero, just like the Lambert's solution. Okay, so this is our goal, right? This is our goal. Okay, so we let u. Okay, sorry. V equal to v xt. W equal to w xt. Okay, v twice continuously differentiable coordinate transformation. Transform. Okay. On an open set U of the xt plane. Okay. So to be a coordinate transform, of course, this transform has inverse. Okay. So that means that the x becomes to function of VW, and the t is the function of VW2. Okay, so you have inverse, of course. Otherwise, it's not coordinate transformation. Okay, and because that it's continuously differentiable, so of course that x and t as function of v and w are also twice continuously differentiable. Okay, so this is the way we have. Okay, so now we let u tilde vw. So we define a new function by coordinate transformation. So we have x vw, t vw. Okay, so this is just. Then of course, then we have u xt can be written by the new function u tilde as v xt w xt. Okay? So alright, so this suppose we have such a twice continuous differentiable coordinate transformation. Right? So we first assume the existence of such a coordinate transformation, right? And try to find it. Okay. So of course we have to say that we have the possibility, all right, to find out such a coordinate transformation. Okay. And so that so we know the relationship between the new function. So the new function is in the new coordinate v and w. Okay? So we will find the spatial coordinate system with w. Okay? And our goal is to eliminate right, the two coefficients here. This is our case. Alright. So now we will do the procedure just like the Lambert did, okay, several centuries ago. So now since, all right, so since the first positive of u with respect to t, now u is expressed as by the u tilde, this one. So we use the chain rule. So we have u tilde v, right? And vt times vt plus w times wt. Okay? This is just a chain rule. So we apply the chain rule. Okay? And ux, the first partial derivative of u with respect to x. So we have u v, of course, and vx plus u tilde x. Okay? So this is the second one. Any questions about the chain rule? Okay? So now utt. Alright, so we take the partial derivative again with respect to t, so utt. So utt, we have to take the partial derivative of this product with respect to t again. So now we apply the product rule as well as the chain rule. So now for this one, first of all, we apply the partial derivative on this part. So we have u v dot vt again plus u v dot w t. This is times vt plus u sub v and vtt. We do the partial derivative of vt with respect to t again. Okay, so this one. For this part, we have u w v dot vt plus u w w dot wt and wt plus u W PT. Okay? So you have a lot of terms here, right? You have a lot of terms. All by chain rule. And actually this is nothing new, right? Just by applying the chain rule. Okay, and the mixed second order partial derivative. Okay, so here, so we have U cubed VV dot Vx plus U VW dot Wx. Okay, and the Vt plus U cubed V dot V Tx. Okay, so this one, finish this one. And then the next part, we have U, UV, V, Vx, plus U, W, Wx, T plus U, W, Dx. Okay, so this is the mixed part. And then finally, the second partial derivative of U with respect to x. Okay, now we have U, Vx plus U, W, X, and the Vx plus V plus Vxx plus U cubed plus V, Vx plus U cubed W Wx and Vx plus U cubed W X and X. Okay, so you have a lot of things. And then you put all things to, okay? The semi-linear PDE 4.6, okay, becomes, all right, so we have A U T squared plus B VT, VT squared, VT and Vx plus C Vx squared times U cubed V, okay, plus 2A Vt and the Wt plus B Vt Wx plus B Vx Wt plus 2 times C Vx Wx and U cubed Vw plus A Wt squared plus B Wt Wx plus C Wx squared U cubed, okay, equal to F cubed V W U cubed V U cubed W. Okay? Alright, so when we substitute all these things into 12.4.6, we will find out a new equation, new PDE. Okay? So this is a new PDE here. Okay. And all terms, alright, related to smaller order partial derivatives were put into the right hand side. So we call it the F tilde. Okay. Okay, so now all right, so to eliminate the two coefficients of U tilde TT and U tilde XX, VV and W. Okay, so to eliminate the coefficients of tilde, we must set. Okay, so we must set A Vt square plus B Vt Vx plus C Vx square equals to 0, and A Wt square plus B Wt Wx plus C Wx square equals to 0. Okay? So we must find V and the W, right? Because V and the W are coordinate transformations, right? And we don't know which one, right? So we have to find them. Okay? So these two equations are needed in order to find the target coordinate transformation, V and W. Okay? So we have that. You can see that the equation take the same form. Okay? Now, so we can do this. Vt divided by Vx square plus B Vt Vx plus equal 0, and A Wt Wx square plus B Wt and W Wx plus equal 0. Now, both equations, okay, both equations has real solutions if and only if, right? If and only if A square minus 4 B square for AC greater than 0, right? This is, we know from high school, maybe junior high school, right? So the equation, okay, has real solution if and only if this is true. Okay, so case 1. The B square xp minus 4a xp c xp greater than 0. means that the semi-IE, the semi-linear PDE is hyperbolic. Okay? So when the semi-linear PDE is hyperbolic, means that this quantity is positive. Right? In this case, now we have two solutions. We have two ODEs as follows: that Vt Vx equal to 2a minus b minus plus, okay, b squared and 4ac, okay, and Wx equal to 2a minus b minus square root b squared minus 4ac. Okay? Because we have two solutions. So one for v coordinate, the other for the w coordinate. Right? Because we need, because this ratio and this ratio satisfy the same quadratic equation. Okay? So you can see that. Okay, so you have these two equations, and we call them as 12.4.7. Okay, so we have the ratio of the partial derivatives here. Now, the two equations, these two equations. So the two equations, okay, in 12.4.7 can be used to determine, all right, the v coordinate curves, as well as the w coordinate curves. Okay? In the xt plane as follows. Okay? Now, because we have, so we can describe, because the new coordinate system v and w are functions of x and t. Okay, so for the v coordinate curve, means that the vx equal to constant, right? The curve is equal to constant. Okay, constant. So we have, right? So the constant we can change it because this is coordinate, right? So you can set coordinate to be 0, 1, or 2, 3, 4, 5, right? So a coordinate curve, just like if our coordinate is linear, so the v coordinate should be a straight line, right? A straight line. But there are a lot of lines. For example, we have x and y, right? And so it's possible that we have a orthogonal coordinate transformation. So we may have x prime and y prime. Okay? So the coordinate line is that the new coordinate, so we have, this is the coordinate line. So the coordinate curve becomes coordinate lines. So it's straight. Okay? So this is coordinate. So this is going from equal y prime equal to 0, y prime equal to 1, y prime equal to 2, y prime equal to 3, etc. Right? You have it. And you may have, let me use another color. So this is okay, so maybe so this is x prime equal to 0, x prime equal to 1, x prime equal to 2, x prime equal to 3, etc. Okay? So this is the new coordinate system. So you have coordinate lines, new coordinate lines. Any questions? Another coordinate system is that if you have a polar coordinate system, so then the other case is that so you have and okay, so you have, for example, so this one is theta equal to 0. This one is theta equal to 45 degrees. Is 41? Okay, so it's pi over 4. This one theta is equal to maybe 60 degrees, something like that, right? So this is the coordinate line, okay? And this one is r equal to 1, r equal to 2, right? So you have, so this is the coordinate curve, right? For r, you have circular, and for theta, you have ray, right? So this is the coordinate curves. You transform the Cartesian coordinate into polar coordinate, right? So this one is for xy. Go to r theta, okay? And this one is xy. Goes to x prime, y prime, by using the orthogonal transformation. Okay? So I just illustrate that they are called coordinate curves. Okay, and so for the v coordinate curves, we know that should be constant. Okay. Constants, just like here. So r, actually r is going to be a constant, right? Constant, and the theta X arctangent, and constant. Okay. Okay. So we have now. So we try to find to solve to find the v-coordinate curves. Okay. And how do we find that? We know that by taking the total variation, taking total derivative, I'm sorry, the total derivative, so we have Vx times dx plus, because it's constant, right? So Vt times dt is equal to zero, right? Right, so by taking total differential. Okay, so that okay, so that the dx dt, okay, the dx dt is equal to minus vt divided by dx, okay. But we have solved vt divided by vx is here, so this is equal to b minus square root of b square minus 4ac to a. Okay. So we have, so this is, so which generate, which govern, or I just say govern, which governs the family of v-coordinate system. Coordinate curve. Okay, is that okay? And this is what is that? This is the first order, the general first order ordinary differential equation, right? First order. So in the xt plane, just like in the xy plane, you can find out a curve. Okay, and to solve such a first order ODE, you have an arbitrary constant, right, as parameters. Okay, so actually, this ODE describes a family of curves because you have an arbitrary constant involved in the general solution. Okay, so this is. Okay, so similarly, okay, for the W coordinate curve, okay, we have Wxt equal to constant. We have again the W sub x times dx plus W sub t dt equal to 0. So this is implies that dx dt is equal to minus W x. So this is becomes to b plus square root of b square minus 4ac divided by 2a. Okay? So which governs, okay, the family of W coordinate curves. Alright? So basically when we solve these two first order ODE, actually we find a proper new coordinate system. Okay, so we're done. Okay, so these two family of these two families of coordinate curves are called the characteristic. Okay, the characteristics of the semi-linear PDE. Okay, and in this case, okay, V and W are called the characteristic coordinate. Of the PDE. Okay. So we conclude that if the semi-linear ODE or PDE in 12.4.6 is hyperbolic in a region. It becomes U cubed V W equal to F cubed V W U cubed V U cubed W by the characteristic coordinate transform. Okay, so this is come to this case. We want to coordinate transformation. And so the example that for wave equation, we have UTT minus C square UXX equal to 0. Okay. So we have A equal to 1. B equal to 0 and C equal to minus C squared. Because they are constant, the coefficients are constant. Okay? And so the B squared minus 4AC is equal to C squared, which is greater than 0. So we know that that's the wave equation is hyperbolic. Always. Okay? It's always because this is positive. And the characteristic coordinate transform V and the W are governed by two ODE, right? So the first one here is 2A B minus, so what is that? C. And C, right? Because B is 0, A is 1, and C is minus C squared. Okay, so you can see. And the other one what is C? Okay, so this implies that we have x minus ct is equal to constant. Okay, so this is, so we have v. Okay, now we have w. All right. So that v equal to and the w. Okay. Or together is the characteristic coordinate transform. Okay, of the wave equation. Okay, and these curves we are called characteristics. Of the wave equation. Okay, so this is for the special cases, right? All right. So you can see that the method of characteristics generalize the idea of the Lambert's solution. Okay, you have that. Okay, so I have to stop here, and I will give you a hangout, and there I will say something about what if the PDE is parabolic or elliptic. Okay, because this is for a PDE which is hyperbolic, right, in certain region. Okay, so we can use the coordinate, characteristic coordinate transformation to transform it into a simple PDE like this one. Okay, you can transform it into such a simple PDE. Okay, so once we get to here, we can apply some elementary method to solve this PDE. Okay, so let's take a break right now.